Hello, I welcome you all to this class. Now today we are going to solve the problem which is related to the regenerations. As you remember in the previous video in which we have discussed about the gas turbine plant, basically the Brayton cycles, and also the method to improve the performance of a gas turbine cycle. So there are the three methods we know, that is intercooling, reheating and regenerations, right? So the regeneration is one in which we are using the that exhaust gases which is coming from the turbine. That exhaust gases is used to heat the air which is leaving the compressor before entering into the combustion chamber, right? So by doing so you can improve the performance of a gas turbine plant. Right now that related to the regeneration methods, we have a one problem. The problem is on the screen, that in a gas turbine plant the compressor takes in air at a temperature of 15 degrees centigrade and compresses it to 4 times, right? The initial pressure with an isentropic efficiency, that is compressor efficiency, is 80%. The air is then passed through a heat exchanger heated by the turbine exhaust gases. So before entering into the combustion chamber, we are heating the air in a heat exchanger by use of the exhaust gases, right? Now the turbine inlet temperature is 600 degrees centigrade. That means the maximum temperature throughout the cycle, or you can say the inlet temperature, right? 600 degree centigrade, and its efficiency is 80%. The turbine efficiency is given 80%. We need to neglect all losses, means neglecting all losses except those mentioned, right? And the turbine, the working fluid through the cycle to have the properties of air, that whatever the fluid is there throughout the plant, that fluid is nothing but the air. So you have to take the properties of a fluid like a air properties only. We need to take properties in the sense that specific heat, gas constant, and the adiabatic index, right? So that is R and Cp and gamma also. Then we have a two cases is there. We need to find out the calculate the thermal efficiency and work ratio of the cycle. First case, if heat exchanger is a perfect, and second case is what, heat exchanger gives 80% of available heat to work, right? So these are the properties you need to take, that R is equal to 0.287 kilojoule per kg Kelvin and the gamma is equal to 1.4. See here the two condition is given in the question, that first you have to consider that the heat exchanger, whatever the heat exchanger we are using for heating the air which is coming from the compressor, that heat exchanger is a perfect. Means when the heat exchanger is a perfect, it means what? It means it gives the 100% performance, right? That means the effectiveness of a heat exchanger in first case we need to take as a 1. But the second case, the heat exchanger gives 80% of available heat to air. Means in the second case, the heat exchanger which we are using, that is not a type of perfect heat exchanger, right? So for that the effectiveness is given 85%, means 0.85%. So first of all, what we need to do, that thermal efficiency you know very well, right? The thermal efficiency is what? That work, net work by heat supply. So net work means what? Whatever the work produced by turbine and the compressor work, means the differences between the turbine work and compressor work will give you the net work. As well as we have to find out the heat supplied, means output is the net work and the heat supplied is the input. So for that we need to know the temperature at the end silent point. Temperature at the silent point means what? That at the end of the compression what should be the temperature, at the end of the expansion what is the temperature. Why? Because the temperature at the and pressure value is given at inlet and the inlet of the compressor and the inlet of the turbine. At the exit of the compressor and exit of the turbine, the temperature and pressure of the air is not given. So we need to find out. So simple it is. First of all we have to draw the TS diagram to understand this question very well, right? So let's start. So just hold on. Yes. So now first of all we will draw the temperature versus entropy diagram for regeneration case. If you remember that so first of all we can say here itself, yes, it's better, yes, right? So this is what you have, a temperature and entropy diagram we are going to draw. That first So this is your temperature on y-axis, and the entropy will be on x-axis, right? So for that you need to draw the two constant pressure line. Okay, so these are the high pressure line and this is the low pressure line. So on that we will see, first of all we have a isentropic compression. If you remember that in previous video we have discussed that how to draw the TS diagram for Brayton cycle as well as for intercooling, reheating and regeneration. If you don't know, you can check the previous videos. The videos in the is on the link, right? So the link on that channel you can find it from here there. So 1 to 2 we have a isentropic compression. First I'll show you the ideal process, right? And then suppose you have added the heat till here, which we call it as a 3, right? This is the inlet of the turbine, and then we are expanding in a turbine at isentropically, right? So this is what you have, a 1, and this is your 2, 3 and 4. 1 to 2 is the isentropic compression and 3 to 4 is the isentropic expansion. But the actual expansion and compression is what? That reversible adiabatic compression. So let's say this is the 1 to 2 dash, right? This is your actual compression in a compressor, and this is your actual expansion, right? 3 to 4 dash, right? Now let's imagine here you have a that is heat exchanger. So what we are doing, that actually it is the method to improve the performance of a cycle. So that regeneration. So in regeneration what we are doing, that this gas which is leaving here, that is not removing it into the open atmosphere, or directly we cannot send it to the compressor, right? So what we are doing, that we are reutilizing this gases. So if you remember the schematic layout, here we have a one pipeline. Through this the exhaust gas will come, and here you have a heat exchanger is arranged, right? So when this air is coming from the compressor after when the air is leaving the compressor after compression, so this air, that compressed air will make it heated by this exhaust gases, right? So when it is heated, its temperature will rise, and then it passes through the combustion chamber. So in that case, that heat supplied in a combustion chamber will be less. It means that you can minimize the consumption of the fuel right now. So that means what? That means we are using this exhaust gases through this here, right? By means of the heat exchanger, it will be, right? So this is like this. So this is the 5, that is T5, right? So here you have a heat exchanger. So when you find out the effectiveness, that effectiveness is what? The ratio of the rise of actual rise of temperature by maximum possible rise of temperature. So actual rise of temperature is what? 2 to 3, and the maximum possible is what? 5 to 3 right now. So this is what you have, means this line is showing that the exhaust gases is passes through the heat exchanger, right? So means this air is heated by this exhaust gases. That is the purpose of this line. It's a TS diagram for the regeneration. Okay, now then already you know 1 to 2 is the isentropic compression, 3 to 4 expansion, 1 to 2 dash is actual reversible adiabatic compression, 3 to 4 dash is the reversible adiabatic expansion, and this 5 is the temperature at a heat exchanger, right? Or you can say the leaving temperature right now. Then first of all we will write down the given data. The given data from the question we can see again. This I'll show you that. Just see, in a gas turbine plant, the compressor takes the air at a temperature of 15 degrees centigrade, means this temperature is given. Okay, that means this temperature is given T1. So here we can write given data. Okay, so this is your T1 is equal to 15 degrees centigrade. Let's convert this into Kelvin. 15 plus 273, that is 288 Kelvin, right? Now then, and compresses it to 4 times the initial pressure, means what? That when it is compressed, its pressure will become P2. So P2 is equal to, that P2 is equal to 4 times of P1. That P1 is initial pressure, right? So it compresses 4 times of the whatever the air is at what pressure it is entering, right? Then the isentropic efficiency of is 85%. Isentropic efficiency means compressor efficiency, and air is heated by the turbine exhaust before reaching the combustion chamber, right? The turbine inlet temperature is 600, means T3 is also given. So we have a further the compressor efficiency, which is the isentropic efficiency. Neta C is equal to 85%, which means 0.85. Alright, and the temperature, inlet temperature of the turbine, which means T3 is equal to, or sometimes they will mention the maximum cycle temperature, so need not to be confused, right? Maximum cycle temperature will always the inlet temperature of the compressor, either it is the intercooling, reheating, regeneration, doesn't matter. So T3 is 600 degrees centigrade, which will be 600 plus 273 means 873 Kelvin. Alright, now and its efficiency is 80%, neglecting all the losses. We are not considering any losses, means mechanical friction and all those things. The properties of air, calculate thermal efficiency. First case is heat exchanger is perfect, and the second one is heat exchanger gives 85% of available heat to air, means in this case the effectiveness will be 1, and in this case the effectiveness will be 0.85, right? So turbine efficiency is given, that turbine efficiency is 80%, which means 0.8. okay, and air properties you can take here, you can write for air, that this property you need to remember always, right? Sometimes they will mention and sometimes they won't. So for properties of air, that is Cp is equal to Cp we don't given, right? So gamma is equal to 1.4 and the R is equal to 0.287 kilojoule per kg Kelvin. Right now, actually the Cp is 1.005, but in this question the gamma and R is given. So whenever the gamma and R is given, you cannot take the Cp as a 1.005, you need to calculate the values, right? If it is not given and they mention that the air, that means the fluid is air which is circulating in a plant, right? So that means that properties of air you have to take gamma as 1.4, R is equal to 0.287 and the Cp is 1.007. But in this question, the gamma and R is specified, so we need to find out the Cp first. Okay, right. So now here, first of all, I'll get Cp value, that is specific heat at constant pressure. Cp is equal to gamma R by gamma minus 1. This is gamma, right? Gamma is the adiabatic constant. So gamma is 1.4 into 0.287 upon 1.4 minus 1. So Cp we got, that Cp is equal to, yes, so Cp is equal to 1.0045 kilojoule per kg Kelvin. As I told you always that whatever the calculation I am doing here, you need to be re-verify, right? Maybe there is a error, but I am sure that error will be the 0.1% right now. Why? Because we already verified all those things, right? So now Cp we got. Now what we need to do, that we have to find out the thermal efficiency. As I told you, thermal efficiency net work by heat supplied means this work minus this work by heat supplied. So T2 dash and T4 dash we need to find, right, for actual. So first of all we will find out the 2 and 1, right? So now you know these all. From here it is, this question is nothing actually, right? The whole gas turbines topic is very easy, right? So in any exam, either it's a university exam or in any conventional exams for your competitive paper, that will, you can score from this topic if the question will come, right? So now you have a 1 to 2 process. So 1 to 2 process is what? That you can say T2 by T1 is equal to Rp to the power gamma minus 1 by gamma, Rp to the power of gamma minus 1 by gamma. Let me check whether we have written the Rp. Yes. So we have a Rp is equal, that is P2 is equal to 4 times of P1. That means that P2 by P1 is equal to 4, and P2 by P1 is nothing but the Rp, that you know already, right? So Rp is equal to 4. All right. Now, so just for that, maybe there is a sometime it may be confused that how it came right now. So T2 is equal to, directly you will do the calculation, T1 times of Rp, and T1 is 288, that is 15 degrees centigrade. So this is 4 to the power gamma minus 1, means 1.4 minus 1 is 0.4 upon 1.4. So you will get the T2 value first. This is the ideal temperature at the end of the compression we got, right? Which you on calculation you will get it 428 Kelvin. Right? Now we need to find out the actual temperature at the end of the compression. So for finding the actual temperature, we will use the isentropic efficiency, that is nothing but the compressor efficiency. So you know that compressor efficiency neta C is equal to what? That is isentropic work by actual work. Isentropic work by actual work. So isentropic means what? T2 minus T1 by T2 dash minus T1, right? So now compressor efficiency is given 85%. So 0.85 is equal to T2, you got 428 minus 288 by T2 dash minus 288, right? So when you cross multiply, so this will be cross multiplied, that is T2 dash, directly I am writing 428 minus 288 by 0.85 plus 288. This is simple mathematics, right? T2 dash is equal to, you will get that 453 Kelvin. Alright, now it means that at the end of the compression, ideal and actual both temperature we calculated. Now we'll move to the expansion side, means on turbine, right? And then we'll find out the actual and isentropic temperature and the actual temperature at the end of the expansion. So for that also we will do same 3 to 4 process, and we will use the turbine efficiency equation. So let's do that. So further you can say 3 to 4 process, okay, which is T3 by T4 is equal to P3 by P4 upon gamma minus 1 by gamma. But you know that P3 is equal to P2 and P4 is equal to P1. So on behalf of that you can say it is P2 by P1, which is nothing but the Rp, right? So directly you can say you need to find out the T4, right? So T4 is equal to, T4 is equal to T3 upon Rp whole power gamma minus 1 by gamma. All the values we substitute, that T4 is equal to, T3 is the maximum cycle temperature which is given in the question, 600 degrees centigrade. So we'll take in Kelvin, which is 873 by Rp is given 4 to the power of 0.4 by 1.4. Gamma minus 1 means 1.4 minus 1, right? So T3 we got. So let's do this. I'm sorry, this is, yes, that T4 we calculated. So this is the T4, by mistake it is right now. So T4 is equal to 587.48 Kelvin, right? 587.48 Kelvin, right? So T4 we got. Now we'll find out the actual, this is the ideal temperature we calculated, right? Now we'll find out the actual temperature. For that we will use the turbine efficiency. That is, turbine efficiency is what? Just reverse of the of your compressor efficiency, means actual work by isentropic work. All right. So now you can say here that neta T is equal to actual work by isentropic work. Right, which is nothing but actual is what? 3 to 4 dash T3 minus T4 dash by T3 minus T4. So turbine efficiency is given, right? 80%. This is 0.8 is equal to T3 is 873 minus T4 dash we have to calculate, by 873, and T4 you have calculated just now 587.48, right? So 587.48, just cross multiply, you'll get the values, right? So on behalf of that, you can say this will be multiplied now. Yes, so T4, yes, you can do the calculation that T4 dash is equal to T3 in the sense 873, right? That is 873 minus 0.8 into 873 minus 587.48. Alright, so on calculation you will get the value T4 dash is equal to 644 point, let me check, I have it good, just hold on, I will do the calculation. 873 minus, yes, so this is the 644.58 Kelvin. Okay, now, so now you can see all the temperature and all temperature at the end of the compression and expansion we got. So now simply we will find out the actual turbine work and actual compressor work. So first of all, I'll write down the actual compressor work. Right, so actual compressor work is what? That is WC is equal to yes, H2 dash minus H1, that is enthalpy, changes in enthalpy, but enthalpy value is not given, enthalpy is Cp dt, right? So that you can say Cp into T2 dash minus T1. So compressor efficiency, actual compressor efficiency is 1.0045. We have calculated at the beginning of the class itself, and T2 dash as well. Where is that? 453, right? So it is the 453 minus 288, that is given in the question. So on calculation you'll get the values. So this is your 299.44 kilojoule per kg, right? This is the compressor work we got. Okay, now we'll find out the actual turbine work. So here itself you can write actual turbine work, right? So turbine work is what? 3 to 4 means WT is equal to T3 minus T4 dash, sorry, first you have to, that is Cp, right? And this is equal to, in terms of the enthalpy, it will be H3 minus H4 dash. That's why actually first you have to write H3 minus H4 dash. No problem, right? Just for the Cp is what? 1.0045, and T3 is 873, it is given in the question, and T4 dash we have calculated just now here itself, that is 644.58. So write down these values, 644.58. So you will get. Sorry, there is a mistake I did actually. So this is your turbine efficiency, that is 299.44 right now kilojoule per kg, and this compressor efficiency I have written wrong. Actually make a correction, please. I'm very sorry that there is a mistake. Okay, so this compressor efficiency is 166. Okay, so this will be in kilojoule per kg. Okay, so don't mind that such mistake can be happen right now. So but all the calculations are same actually. Okay, so this turbine efficiency you got, this is WT. Okay, so WT we calculated, which is your 299.44, and compressor efficiency is 166. There is a mistake, by mistake I have written right now. then what we need to do, that we need to find out the net work, right? So net work, how you get that? Net work is equal to turbine work minus compressor work. So this you can see here, that we can write first net work output, right? Net work output, right? So net work output is what? That W net is equal to WT minus WC, that is turbine work minus compressor work. So turbine work, just now we see that is 299. Let me check again, otherwise mistake. 299.44. So this is 299.44 minus compressor work is 166. So on calculation, you will get, this is a 64.64 only, right? This is, no, actually it is not 64. 299.44 minus 166 point. So it will be is it 299 or 229? 229. Sorry, there is a, it's a 229, right? Make a correction. Let me show you that it's a 229. 1.0045 into 873 minus 644.58. Yes, this is 229. There's a mistake, little mistake we did. Right now. So now you can say here, that is this is the 229. Make a correction, please. This is 229.44 minus 166. So it will be 229.44 minus 166 is equal to 63.44. 63.44. Or you can take it as a 64 kilojoule per kg, right? So this is your net work. There's a two mistake we encountered today, right? That is net work. Now we need to find out the heat supplied. That is the heat supplied. This is your input, heat supplied, right? So for finding the heat supplied, what we need to do, actually it is not a normal gas turbine, right? It's a regeneration. So in regeneration we have to see which temperature we'll see. Let me show you the TS diagram. So this is your TS diagram, right? Actually if I remove this heat exchanger, that is regenerator, right? So what will happen? That means the heat is supplied from T2 to T3, but this gas, this exhaust gases is utilized to heat the air which is coming from the compressor side, right? So now the heat supplied is not from here, but we'll take it from the 5 to 3, right? Now why? Because this temperature we won't use, right? So that this temperature is not directly entered into the combustion chamber. This temperature is entered into the temperature. Is it or not? This is why we are using the heat exchanger. That's why, that is regeneration, right? So heat supplied, for that heat supplied we need to know the T5, right? So for that we will use the concept of what is given, heat exchanger, right? So first case you can say when heat exchanger, HE is the heat exchanger, is perfect. So when the heat exchanger is perfect, that is, which means effectiveness is equal to 1, right? That you have to remember. Now, so effectiveness is what is of a heat exchanger is what? Effectiveness is equal to actual rise of temperature, actual rise of temperature of air upon maximum possible rise, maximum possible temperature rise, right? Maximum possible temperature rise. So this we can say effectiveness is equal to actual temperature rise is what? That actual temperature rise is nothing but, you can see, from 2 to 3, but maximum possible rise is what? 5 to 3. So now you can say the effectiveness equation in that format. So this is what? T3 T5 to T2 dash by T4 dash to T2 dash. Is it or not? When it is the perfect intercooling, right? So now you can substitute and get the T5 value. So this is your effectiveness is what? 1. T5 we have to calculate minus, it's very, size is very less. So T2 dash you have calculated, which is 452.7, by T4 dash we have calculated 644.54 minus 452.7. So cross multiply, you will get the T5. So T5 is equal to what? That is 644.54 minus 452.7 plus 452.7. So T5 we got, which is your 644.58 Kelvin. T5 we got. Now you can find out the heat supplied, right, in case of the perfect intercooling, right? So first of all, you can say here itself, that is heat supplied for first case. So heat supplied is what? That heat supplied QS is equal to CP T3 minus T5, only 5 by using the heat exchanger, means T2 we are not using, right? So 1.0045, T3 is 873, which is given, and T5 just now we have calculated 644.58. So let me do this, otherwise again we'll do mistake. 1.0045 into 873 minus 644.58. So yes, same, that is 229.44 kilojoule per kg. So this heat supplied you got, that is input for perfect intercooling. Now thermal efficiency you need to find. So neta thermal is equal to what? W net by heat supplied. So W net is what? The turbine work minus compressor work, which you have calculated 64. Okay, so let's write, that is 64 by 229.44. So 64 divided by 229.44, 0.278, right? It means that here only we can write 0.278, which is thermal efficiency for perfect intercooling of a gas turbine plant with regeneration. In this particular case, it is 27.8%, right? This is first answer. Now we have to calculate the work ratio, right? So you can write first, that is work ratio. Work ratio, you know that what? Net work by turbine work. Is it or not? Okay. So work ratio you have a, let's say that work ratio we are using W dot R is equal to W net by WT. Okay, so work ratio will not change, either you are using the perfect or imperfect. There is a relation between net work and turbine work only. There is no use of the heat supply right now. So that's why the work ratio will not be changed either in the perfect cooling or in imperfect cooling, right? So W net you got, which is 64, and this is the 229.44, that equal is here, right? So the work ratio will be 0.27. This is same, yes. So 0.278, right? That is also right. Now next we have a case when the heat exchanger is not a perfect, then the available heat of air is given, that is 85%, means that this time we need to take the effectiveness of a heat exchanger as a 85%, which is 0.85, right? So here the second case you can write, that is second case is it is B, that when effectiveness is equal to 85%, right? 85%. So effectiveness is what? That is actual rise of temperature, right, by maximum possible rise in temperature. So you can say in this format also, delta T is of actual by delta T of maximum. Maximum means what? That 4 to 2, and actual is what? That 2 to 4, 5 to 2, right? Okay. So now here itself you can write, this is the T5 minus T2 dash, this is actual from 5 to 2, and 4 to directly from end of the expansion to the compressor end, right? That is T4 dash minus T2 dash. Okay. Now so you can again you have to find out the T5, but here the effectiveness will be 0.85. let's do that. That is 0.85 is equal to T5 you have to calculate, T2 dash is 452.7 by T4 dash is 644.54 minus T2 dash same 452.7. so when you cross multiply you will get the values, that is T5 is equal to, in this case 615.8 Kelvin, right? So this much of heat we got in case of the means when the heat exchanger is not a perfect, right? So now we need to find out the heat supplied. So here, yes, wait, just wait, it's hardly more 2 minutes we have. Heat supplied. So heat supplied, so heat supplied, that is QS is equal to Cp. From where to where you are supplying the heat? That is T3 to T5. So Cp is 1.0045 and T3 is same 873, and T5 we calculated which is your 615.8 Kelvin. So on simplification you will get, let's 1.0045.873 minus 615.8. okay, yes. So this is the 258.35 Kelvin, sorry, kilojoule per kg, yes, right now. So this is the heat supplied you got. Now further you need to find out the you can say the thermal efficiency when the effectiveness is this. So neta thermal is equal to W net by heat supplied, that is QS. So W net is what? 64 we already calculated, and heat supplied is this 258.35. So on calculation we'll get the thermal efficiency as a 0.227, which is nothing but the, or you can say 22.7%, right? So if you compare this, that when the heat exchanger is perfect, the thermal efficiency of the plant is more, and when the heat exchanger is not a perfect, means that some heat is lost, right? So that is what, that efficiency of the plant is decreased, which is become 22.7, but in perfect heat exchanger that efficiency we got the 27.89. Is it or not? Means there is a loss of 6%, near about 6% of efficiency is lost in case of the imperfect heat exchanger, right? So now that this is your second answer, right? Then you have a work ratio. Work ratio will not affect, but I'll show you that W net by WT. W net is 64 and this is 229.44. This values I remembered, why? Because I did mistake 2 times right now. So this is the 0.2789. So this is how we can solve the problem which is related to the methods of improvement, right? So in next class we will see some more problem. So please do like, subscribe and share this channel. Thank you.